Alright, so the next thing we're going to do is we're going to review phases. There's a couple things you need to know. First of all, you need to know obviously the basic phase changes from a solid to a liquid. If you go in that direction, we call it melting. If you go in the other direction, it's freezing if you go from a liquid to a solid. Liquid gas transition, one direction is vaporization. If you go in this direction, you have vaporization. If you go in the other way, you have condensation. If you go from a solid to a gas, that is called sublimation. A gas to a solid is called deposition. Remember the S, L, and G rule. The way we move substances from a solid to a liquid basically is we add energy to a substance to move it from a solid to a liquid to a gas. So we say the delta H value is positive when you're going this direction. If you go in the other direction, the way we make that happen, going from a liquid to a gas, or a condensation, or going from a liquid to a solid, which is freezing, we say that we're losing energy, so the delta H value would be negative. So that's the difference between endo and exothermic phase changes. So we have to learn how to interpret these on a heating curve and a phase diagram. So kind of summarizing what we just learned before, you have three endothermic ones, which are sublimation, vaporization, melting. Fusion is a fancy way of saying it. Then we have three exothermic ones, deposition, condensation, and freezing. When you go and look at heating curves, here's a typical heating curve that you're expected to interpret. A couple things you need to be aware of. Solids are always represented by the lowest level on a heating curve. So solids would be here, liquids are in the center, and gases or vapor are right there. The flat lines you have to pay particular attention to, like between A and B, we say the solids and the liquids are in equilibrium. That means at that point the temperature is not changing. That's why you see the line is flat, it has no slope, because that's what we call the melting point. That's the melting point of the substance. All the energy that you're adding to it at that point, because you're adding heat as you go in this direction, is going to separate the molecules. Because we say in a gas, the molecules are in a fixed position, whereas a liquid, they're in a loose position, but very close. Once everything turns into a liquid, you get to point B. Then any energy or heat that you add this direction increases the temperature of the liquid. Then when you reach point C on the graph, point C from point D is represented by, that is where the normal boiling point at 1 atmosphere occurs. We say the liquid, and the vapor are in equilibrium at this point. As you're increasing the heat, here on the bottom, the amount of heat supplied is increasing right here. We can get it to work. Oops, I lost it. If you look right here, let's try this. If you look right here, the liquid and the vapor we say are in equilibrium, because as we're going this direction, it's increasing the amount of heat is increasing as we go this direction from C to D. So we say basically all the energy is going into increasing the distance between the molecules, just like the same thing at A and B. All the heat that's being added there isn't changing the temperature, it's increasing the difference, because the difference between a solid, liquid, and a gas is basically the amount of distance between the molecules, and the way you increase the distance is increase the kinetic energy or add heat. During the phase changes, all the energy added goes into separating the molecules between A and B and C and D. Typical heating curve. Alright, here's an example of a cooling curve. The same thing's occurring. You have the gas is always the highest part of the curve. The molecules are very far apart. You remove some of the energy, the molecules get closer together. That's what happens in this part of the curve, the gas-liquid equilibrium. Once they all become closed in, like you see right here, in proximity to each other, the liquids, then all the energy that's being removed changes the temperature of the liquid to a certain point. At this point we get to what's called the freezing point. That's where, and that's the flat line we saw on the graph when we did our lab with the BHT. All the energy is going to stacking, arranging the molecules, and not changing the temperature of the substance. So this right here is the freezing point. Once they all solidify, then you'll see the temperature drop again, because now you're just changing the temperature. All the energy that you're removing is removing the energy from the substance. So it's important to remember to be able to identify those parts. Here, if you look at it for water, you notice, again, this is my solid, liquid, my gas. Phase change here is melting. Phase change here is vaporization. Notice the line for vaporization is a lot larger than the line for melting. It takes more energy to separate the molecules a greater distance, that you have to move them from a liquid to a gas. Therefore, it takes more energy. That's why this line is longer. You should be able to recognize the freezing and the vaporization or boiling points on one of these graphs and interpret it. Know what's happening at each stage. That brings us to the last part. Phase diagram is pretty simple. It's the relationship between pressure, and temperature. Basically, the three phases of substances and how they change given a value for temperature and pressure. So if you look right here, solids are always here, liquids are always represented here, and gases are always represented here. There's some key points that you have to be able to interpret on a phase diagram. If you look right here, again, we have solid, liquid, and a gas. If you look, you need to know where the phase changes occur. For example, going from a solid, from this point to here, to a liquid we know is melting. Same thing if I had a point here and travel this direction to another point here, going from a liquid to a solid we know is freezing. If you go from a point here and travel across this way, that's called vaporization, going from a liquid to a gas. Again, a lot of this is common sense. If you have a point here and you travel this direction, that's condensation. Down here we have the other two phase changes, sublimation and deposition. Key parts to know on a phase diagram: one is the triple point right there. That is where all three phases of matter exist. The critical point is right here. That's the temperature where only gases exist, no matter how much pressure you add. Normally you can increase pressure and kind of push molecules together and cause them to form a liquid, but there's a certain temperature, the critical temperature, which I kind of drew a funny looking line, but the critical point is that the temperature past there is where only gases exist. The equilibrium line, so if you say equilibrium between a solid and a gas, a solid and a liquid, is represented by that kind of line right there. The equilibrium between the liquid and the gas is represented by that line right there. One of the other key things you need to be able to interpret is the slopes of the line representing the boundary between liquids and solids. If it has a positive slope to it, like here, CO2 has a positive slope, it means that the solid is more dense than the liquid. One of the things we know is water, for example, is one of the only substances that is more dense as a liquid than a solid. The way we actually tell that is by looking at the slope of this line. If you can draw it, circle it, or whatever, right here, that has a negative slope. So the slope right there with the pressure, notice it has a negative slope to it, so therefore it makes the substance less dense as a solid than a liquid. And that's pretty much all you need to know to interpret the phase diagrams and a heating or cooling curve. That's pretty much it for the AP exam. All right? Good night.